We are going to be reading Chapter 28, Section 1, Tools of Astronomy, found on page 747. The best tool, and in most cases the only tool that astronomers can use to learn about the universe is the light that comes on Earth from distant objects. Apart from a few solar systems, objects that have been sampled by direct probes and particles are fragments that have made their way into Earth's atmosphere or Earth's surface. There is no other way to study the cosmos except to analyze the radiation emitted from it. Therefore, it is necessary to understand this radiation. Radiation. The radiation from the cosmos that scientists study is electromagnetic radiation. Electromagnetic radiation consists of electric and magnetic disturbances traveling through space as waves. The human eye can sense only a limited range of all the various wavelengths of electromagnetic radiation. This range is called visible light. Electromagnetic radiation includes not just visible light, but also infrared and ultraviolet radiation, radio waves, microwaves, X-rays, and gamma rays. You may be familiar with some forms of electromagnetic radiation. For example, ultraviolet radiation causes sunburn, and X-rays help doctors observe internal injuries and diagnose bone diseases. All the types of electromagnetic radiation arranged according to wavelength and frequency form the electromagnetic spectrum, illustrated in Figure 28.1. Electromagnetic radiation is classified by its wavelengths. Wavelength is the distance between peaks on a wave. You can see in Figure 28.1, the red light has longer wavelengths than blue light, and radio waves have much longer wavelengths than gamma rays. Electromagnetic radiation also can be classified according to frequency, which is the number of waves or oscillations occurring per second. The visual light portion of the spectrum has frequencies ranging from 4.3 times 10 to the 14th power to 7.5 times 10 to the 14th power. Hertz frequency is related to wavelength by mathematical relations. C is equal to AF, where C is the speed of light, 3.0 times 10 to the 8th milliseconds. This symbol is the wavelength, and F is the frequency. Note that all types of electromagnetic radiation travel at the same speed. Telescopes. Objects in space emit radiation in all portions of electromagnetic spectra. The ability to modify telescopes was different with different detectors and mirror shapes to observe all wavelengths, especially those the human eye cannot detect, is just one of the benefits of using a telescope. Another benefit is that a telescope collects electromagnetic radiation from a distant object and focuses it at one point where the image of the object can be studied or recorded. The human eye does the same thing with visible light, but the eye is much more limited. A typical human eye pupil has a diameter of up to 7 millimeters, and then it is adapted to darkness, whereas a telescope might be as large as 10 meters in diameter. The area of the opening through their electromagnetic radiation enters determines the collecting point of a telescope. The larger the opening, the more electromagnetic radiation that can be gathered. A telescope's ability to collect a large amount of electromagnetic radiation allows astronomers to observe faint or weakly emitting objects. A third benefit of telescopes is that they allow astronauts to use specialized equipment. A photometer, for example, is used to measure the intensity of a visible light. A fourth benefit is that telescopes can be used to make time expenses with the aid of cameras or other imaging devices. In time exposures, electromagnetic radiation is collected over a long period of time. With visible light, the human eye photographs what it sees about 10 times per second, so an object too dim to be perceived in 1/10 of a second cannot be seen. This is why telescopes are able to detect objects that are too faint for the human eye to see. Refracting and reflecting telescopes. Two different types of telescopes are used to focus visible light. The first telescope, invented through around the year 1600, used lens to bring visible light to a focus and are called refracting telescopes, or refractors. The largest lens on such a telescope is called the objective lens. Figure 28.2a illustrates how simple refracting telescope works. In 1668, a new telescope was designed that used mirrors. Telescopes that bring visible light to a focus with mirrors are called reflecting telescopes, or reflectors. Figures 28.2b illustrates how a simple reflecting telescope works. Although both refracting and reflecting telescopes are still in use today, the majority are reflectors. Most telescopes used for scientific study are located at observatories far from cities' lights, usually as high elevations where there is less atmosphere overhead to blur images. Some of the best observatory sites in the world are located high atop mountains in the southwestern United States, along the peaks of the Andes Mountains in Chile, and on the summit of Kaunuki, the gigantic volcano on the island of Hawaii. Telescopes at other wavelengths. In addition to using visible telescopes, astronomers observe the universe at wavelengths that the human eye cannot detect. For all telescopes, the goal is to bring as much electromagnetic radiation as possible to a focus. Infrared and ultraviolet radiation can be focused by mirrors in such the way as visible light. X-rays cannot be focused by normal mirrors, and thus special designs must be used. Because gamma rays cannot be focused, telescopes designed to detect the extremely short wavelengths of this type of radiation can determine little more than the general direction from which the rays come. Figure 28.3 shows a radio telescope consisting of a large dish or antenna which resembles a satellite TV dish. The dish plays the same role as the primary mirror in a reflecting telescope by reflecting radio waves into a focus above the dish. A receiver converts the radio waves into electromagnetic signals that can be stored in a computer or for analysis. A process called informatory, which has been used with radio telescopes for a number of years, is now being used to apply to other telescopes as well. Interferometry is the process of linking separate telescopes together so that they act as one telescope. The detail in the images that they produce improves as the distance between the telescopes increase. One of the best known examples of this technology is in the Very Large Array near Socorro, New Mexico. Satellites, probes, and space-based astronomy. Astronomers often have to send their instruments into space to collect the information they seek. One reason for this is the Earth's atmosphere blocks infrared radiation, ultraviolet radiation, X-rays, and gamma rays. In addition, when Earth's atmosphere does allow certain wavelengths to pass through the images, though the images are blurred. Another reason for sending instruments into space is to make close-up observations and even obtain samples from nearby objects in the solar system. Since the late 1960s, American, European, Soviet, later Russian, and Japanese space programs have launched many space-based observatories to collect data in different wavelengths. One of the best-known space-based observatories, shown in Figure 28.4, is the Hubble Space Telescope, which was launched in 1990 and is scheduled to operate until 2010. HST was designed to obtain sharp visible light images without atmospheric interferences, and also to make observations in infrared and ultraviolet wavelengths. Other space-based telescopes, such as the Far Ultraviolet Spectroscopic Explorer, the Chandra X-ray Observatory, and the Spitzer Space Telescope, are used to observe other wavelengths that are blocked by Earth's atmosphere. Spacecraft. In addition to making observations from above Earth's atmosphere, space-based exploration can be achieved by sending spacecraft directly to the bodies being observed. Robotic probes make close-up observations and sometimes land to collect information directly. Probes are practical only for objects within our solar system. Because the stars are much too far away, the robot Sojourner, part of the Pathfinder probe, explored Mars for almost 3 months in 1997. More recently, the twin robots Spirit and Opportunity conducted scientific experiments in Mars in 2004. Human spaceflight. Exploring objects in space have been a top priority for scientists, but they have also been very interested in exploring the effects of space, such as weightlessness. The most recent human explorations or studies have been accomplished with the Space Shuttle program, which began in 1981. The Space Shuttle provides an environment for scientists to study the effects of the weightlessness of humans, plants, and growth of crystals, and other phenomena. However, because shuttle missions last a maximum of just 17 days, long-term effects must be studied in space stations. A country space station called the International Space Station, shown in Figure 28.6, is the ideal environment to study the long-term effects of space. Human habitation and research abroad. The International Space Station began in 2000. Spin-offs. Space exploration programs have benefited our society far beyond our increased understanding of space. Many technologies that have originally developed for use in the space programs are now used by people all over the world. Did you know that the technology from the space shuttle's fuel pumps led to the development of pumps used in artificial hearts? Or that the Apollo program led to the development of cordless tools? In fact, more than 1,400 different NASA technologies have been passed on to the commercial industries for common use and are called spin-offs. Each year, new technologies are developed that not only benefit astronomers in space exploration, but society also.